All right, so we are in 5.2. And in 5.2, we got a lot of old rules that we're supposed to have kind of already learned from Algebra 1. I'm going to go over them again with you because they are so important. And the rules that we learned in Algebra 1 are still going to apply in Algebra 2. The only difference is we're going to use them with a little nastier numbers, not really that bad, especially today. But the rules always in math are, if it's going to be a rule, it has to work every single time. Does not matter the number. So some of the rules that we're talking about are these. If you had some number to the m power and you times it by that same number but to the nth power, that actually is the same thing as a m times n. So what happens is,
Mr. Moran.
Sorry. Oh, I got you. Yep. A plus m. Sorry. I got so excited about the new rooms, I forgot. Thank you. So there we go. If you have a to the m times a to the n, it becomes a to the m plus n. And that should make sense to you guys. Like, none of these rules were just made up because someone said that's how they feel like this should be. There's no feelings involved in math. It is what it is, right? So like, if you think about it, this means if you take x squared and you times it by x to the third, that will get you x, whoops, x to the fifth power, which should make sense to you because what does x squared mean? It means x times x times, that's that times right there, right? This right here was broken out into this, and this becomes times x times x times x, which if you count it, 1, 2, 3, 4, 5, 5 x's times each other is really the same thing as x to the fifth. So that's where that rule came up from. Something I want to talk to today, because we're on this rule, is I'm going to ask you a question. Tia,
Yeah.
how many x's are there in this one?
5.
Sierra. Sierra, are you with me? It doesn't really matter. Orest, you with me?
Yes.
How many x's are in this one?
3. 5.
This one. 5
1.
x's here. How many x's here?
5.
So this is 5 x's. This is not 1 x, guys. This is 5 x's. What's the difference between these 5 x's and these 5 x's?
In x to the fifth, you're multiplying x by itself 5 times, but in 5x, you're multiplying x by 5.
Close, Kelly. There are actually 5 x's. So a power is repeated multiplication. What is multiplication?
Oh, addition.
So it's still 5 x's. But the big change is there's a plus sign between these guys. Whereas up here, there's a multiplication. So there's still 5 x's here. There's still 5 x's here. But the way that we're doing between the x's is what changes. This is repeated addition. This is repeated multiplication. That's what we need to start recognizing. Okay? This is not 1x. There are 5 x's here. That's why, again, when we have 5x plus 6x, we have 11x. Because this is literally 5 x's added together. This is 6 more x's, total of 11 x's added together. All right, does that make sense?
Yeah, it makes sense.
A m over a n. One way, the way they want to do is this is a m minus n, and there's sometimes that we want to use this. Today we will use that actually. If you have a over m and divided by a to the nth, you can subtract the 2 powers. Normally, if it's something like this, x to the third over x to the fifth, we don't do this really. What we do is we say, hey, there's 3 x's up here multiplying to each other, but there's 3 of them. There's 5 of them down here. So 3 of these x's will cancel 3 of these out. So goodbye. And 3 of these will be canceled out, leaving me with 1 left over. So my final answer of this would be 1 over x squared. But sometimes we want to know this rule, and later on today I'll show you why we want to use that. Maybe these are fractions, and it will make it easier if we know how to just subtract them like that. By the way, this still works for this. This would turn in x3 minus 5, which would turn into x to the negative 2. And that kind of is a good transition for the next rule I would talk about. Does anyone know what happens when you have a negative exponent? So a negative exponent does nothing to this number, changing it positive or negative. Does nothing to that. All it does is it moves its location. Huh?
It makes it smaller.
Not necessarily, Orist. So what it does is the negative just changes its location. So thinking of this as a fraction, where whatever is touching the negative exponent just switches its location. So the x squared would go down to the bottom like this. And so this right here is the same thing as that answer that I got. I'll explain that rule a little better right here. If I have x to the negative 3y, remember any number can be written as a fraction. So the negative 3 is only touching the x. So that negative 3 actually sends that down. The y stays up top, and then I get x to the third. And when you move it locations, the negative is gone. So it's no longer a negative 3, it turned into a 3. And that would be my final answer for this one. If I had y x to the negative 4z, the y in the z, even if it has a 2, this has a 7, the y is a positive, so it's not going to move locations. The z is a positive, it's not going to move locations. This has a negative with it, so it is going to move, and it's going to move up. And so this would be x to the 4th y squared over z to the 7th. So all a negative exponent does is just move it either from the top to the bottom or the bottom to the top. So top to bottom, bottom to top, that's the only thing a negative does, is move its location. And when it moves it, notice the negative is no longer with it. Does that make sense?
Yeah.
If I have a to the m to the nth, what does that equal? So this is called power to a power. What is the rule for that one?
You multiply the powers.
Yes, you multiply them. So this becomes a m times n. And that again makes sense, because if I had x squared to the 3rd power, this turns this, what does this mean? This means you're going to have x squared timesing itself 3 times. If you look at it like that. So this becomes x squared times x squared times x squared, right? X squared timesing itself 3 times. What does x squared mean? That means x times x. That is this broken out right here, right? Times, break this out, x times x, times, break this out, x times x. And if you look at that, 1, 2, 3, 4, 5, 6, or x to the 6th. And the rule was you just multiply these two numbers. What's 2 times 3? 6. So you can skip all this work if you know the rules. So like x to the 3rd to the 5th just turns into x to the 15th. You multiply these two. And again, what I try to show you in math, I don't try to confuse you. I'm trying to make it so that you see the differences between them. We can't get rules mixed up. Like when I write this rule, I have to pay attention to the details. What is in between the A and the B?
Multiplication sign.
So when I do that, I am free to distribute this, and I'm telling you that this becomes A to the M times B to the M. And that is cool to distribute this M because there's a multiplication between these two. So even if I had like 2x to the 3rd power, that would become 2 to the 3rd x to the third, or 2 to the third, which is 8 x to the third. That is perfectly the answer for this. This would be the simplified version. Now, what I'm telling you is 2 plus x squared. What's between the 2 and the x? Hello? What symbol is between the 2 and the x?
Addition.
And so guess what we cannot do with this 2? We cannot distribute it, and that would be wrong. What do we have to do here? 2 plus x times 2 plus x. And what do we have to do when we have something like this? We have to distribute it out. Now, normally we would write it as x plus 2. I wrote it as 2 plus x because if you look, 2x to the third looks very similar to 2 plus x to the third. And so you can see why kids try to distribute this one and they end up getting it wrong for a long time until they start taking some pride in their work and seeing the difference between this, because it's very subtle. It's only that little plus sign. It's only, and in fact, this one doesn't even show the sign. It's understood to be a multiplication. Do you guys get what I'm pointing out to you and see the differences between the two?
Yeah.
You have to know when to use rules and when not to use them in mathematics, or it turns into a massive just pile up of just bad. It does not work when you do not use the rules right. All right, so here we go. Here's how we're going to use these rules, and they are going to look a little uglier today, but what was the rule? And I don't know what you guys, because I don't see your work too much. I mean, I get to see it uploaded, but it's hard for me to kind of look through every picture and talk to you individually about it. I hope that you are not writing math left to right. Don't work like this. Work up and down. It's much easier to keep. Then you can see step 1, 2. I've been kind of telling my students that because this year's been the worst with seeing kids write this way. It just, everything gets jumbled up and it's hard to follow. Waste paper. You recycle it if you're worried about the trees, which is I am too. Go ahead, recycle the crap out of that paper, but stop writing left to right because you want to save paper. It drives me crazy. All right, so since we have the same base, what was our rule? We're going to add the exponents. So we're going to take, I'm okay with you taking this to the side. I'm going to take 5, 6 and add it to -1/3, but I'm going to work this problem up and down. I'm going to say, hey, I need you to become a 6 because to add fractions, they have to have common denominators. So 5, 6 is good, plus a -2, 6, which is going to turn into a 3, 6. 3, 6 reduces to 1/2. See how you can see step 1, step 2, step 3, step 4, and it's very easy to follow. Whereas if I have 5, 6 plus a -1/3 equals 5, 6 plus a -2, 6 equals 3, 6 equals 1/2. There's so many equal signs up here. It just kind of gets confusing. There's so many fractions in each. So it's nice and easy to, I feel, my brain likes the look of this better where I can see that's step 1. Then I went to here, then I went to here, and then I went to here. Much easier for me to follow. So all this, when I added them together, became a 1/2. So I have 81 and 1/2. And what did we learn from last 5-1? What did we learn that we can change this? This is power form. How can we change that to radical form? Well, we learned that the 2 goes on and becomes my index here. So since it's a 2, I don't have to write it. I put the base, which is 81, and then I put the power right here. But since it's a 1, I don't have to write it. So this would be technically a 2, which I wouldn't write. This would be a 1, which I wouldn't write. So really what you would see is the square root of 81. And the square root of 81 is 9 would be my final answer. Did that make sense?
Yeah, so as long as they're the same number variable, you can, like, if
Bases
both-
are the same. Add the exponents.
okay.
Right? A to the m times a to the n. Now notice it's not plus sign in between here, right? So if I had 2 to the third plus 2 to the second, this does not equal 2 to the fifth. This has to be a multiplication sign. If there was an addition, you would actually have to do 2 to the third, find its number, do 2 to the fourth, find its number, and then in the end add them. So this would actually be 8 plus 4, which would be 12, which is much different than 2 to the third or 2 to the fifth, which is 32. You know, those are not the same. So it has to be a multiplication sign between them. I get it. Math sucks for that reason, right? This looks so similar to this. The only difference is these signs. Those, if you can't tell that the addition and subtraction have different rules than multiplication and division, you need to learn that real quick. Did that make sense, Kelly?
Yep.
All right. Now, if it's me, I'm going to solve this problem by doing this stuff inside the parentheses first. So really, as soon as I see this x, this is x to the first power. This 3 does not belong to it. So that's x to the first, and that's x to the half. And I know that if I have a to the m over another a to the nth, I can actually take this and make this a to the m minus n. So what I can do here is I can make this become x to the 1 minus a half, which hopefully you guys can do in your head and realize that that's x to the 1/2. 1 minus 1/2. And then right next to it, I'm going to do y to the third, and all of this is being raised to the 2/3 power. Did I lose anyone on that step? Next, when we had a power out here, oops. When we had a power out here, we said we can distribute this. And so really, when we do a power to a power, we're multiplying them. So this becomes 1/2 times 2/3. And per multiplying fractions, we can cross simplify. 1 over 3. So this turns into x to the 1/3. And then 3 over 1, that's from right here, times 2/3. That's by taking it to this power and distributing it. I can cross simplify again. This turns to a 1, and then I end up with 2 over 1 or 2. So y is to my second power. And then finally, we don't like the way this looks. We want to change that to radical form. So I'm going to pull the y squared first. And then I'm going to do, this is the index, so it's going to be the third root of x. And so that would be my final answer for that one. Are there any questions on what I've gone over so far?
No.